Welcome to AP Precalculus. Today, we're diving into a fundamental concept: how two quantities change in tandem. By the end of this video, you will be able to define the average rate of change, calculate it from various representations like tables and graphs, and interpret its meaning within a given context. Essentially, our goal is to understand how we can precisely describe the relationship between two changing quantities. So, what exactly do we mean by change in tandem? It simply means that as one quantity changes, another quantity changes along with it in a related or dependent way. These two variables are connected. In precalculus, we model these relationships using functions. We write this as y equals f of x, which reads y is a function of x. This notation means that for every input x, there is exactly one output y. Let's look at some simple examples. The number of hours you work determines your paycheck. Here, hours worked is the input, and money earned is the output. Another example is time and distance. As time passes, the distance a moving object travels changes. Before we calculate anything, there's a crucial step that is a must-do habit for AP Precalculus: defining your variables, including their units. This helps you think clearly and avoid errors. Always define your variables. Think about which variable is independent, or the input, and which is dependent, or the output. The output depends on the input. Then assign appropriate units. Let's work through an example. Imagine a tank is filling up. We can define T as the time that has passed, measured in minutes. We can define V as the volume of water in the tank, measured in liters. In this scenario, the volume of water V depends on the time T. As time passes, the volume changes. So, time t is our independent variable and volume v is our dependent variable. We would write this relationship as v equals f of t. Getting into this habit of defining variables will make interpreting your calculations much easier and is essential for writing clear and accurate AP responses. Now that we know how to set up the problem, let's learn to calculate how fast one variable changes relative to another. This is called the average rate of change. The average rate of change tells us, on average, how much the output y changes for every 1 unit change in the input x over a specific interval. In other words, it's a measure of speed. We calculate this using the formula. The average rate of change from x equals a to x equals b is the quantity f of b minus f of a, divided by the quantity b minus a. The numerator, f of b minus f of a, represents the total change in the output. The denominator, b minus a, represents the total change in the input. So it's simply change in output over change in input. Let's apply this with a mini example. We won't use a specific function, just some data points. Suppose we know that for a function f of 2 equals 10 and f of 6 equals 22. Let's find the average rate of change on the interval from x equals 2 to x equals 6. Following our formula, we'll plug in the values. We'll have 22 minus 10, all divided by 6 minus 2. This simplifies to 12 divided by 4, which equals 3. So what does this number 3 mean? If we define units, it would be y units per x unit. In this context, it means that on average, for every 1 unit increase in x on the interval from 2 to 6, the value of y increased by 3 units. The average rate of change tells us the typical or overall speed of change. We can visualize the average rate of change on a graph. In fact, on a graph, the rate of change tells the whole story. On a graph of y equals f of x, the slope of the curve tells us how f of x is changing. A steep upward-sloping curve means the function is increasing rapidly. A flatter upward-sloping curve means it's still increasing, but at a slower rate. A perfectly flat or horizontal line indicates zero rate of change, and a downward-sloping curve shows the function is decreasing. Let's put this together with our formula. The average rate of change between 2 points on a graph, a f of a and b f of b, is geometrically represented by the slope of the straight line that connects them. This line is called a secant line. You might remember the slope formula. M equals change in y over change in x, or m equals delta y over delta x. This is exactly what our average rate of change formula calculates. So, on a graph, the average rate of change is the slope of the second line. In AP Precalculus, you'll often encounter a specific way of phrasing your interpretation. The template for the average rate of change is, for each additional 1 unit of x, the output y changes by your calculated value units on average. This template ensures you use the words on average and per 1 unit of x, which are both critical for a correct interpretation. So far, we've talked about different ways to represent a changing relationship: context, story, tables, and graphs. Now let's connect these to equations. A key skill in AP Precalculus is to be able to seamlessly switch between all 4 representations: the real-world context, a table of data, a graphical picture, and an algebraic equation. Let's look at how we can identify 2 important types of functions from a table. If a relationship has a constant difference in the output, y, for every 1-step change in the input x, then that relationship is linear. A linear function has a constant rate of change, which is its slope. For instance, if y goes up by 5 every time x goes up by 1, that's a constant rate of change of phi. On the other hand, if a table shows that the output y is multiplied by a constant factor for every 1-step change in the input x, then the relationship is exponential. For example, if y is always doubling as x increases by 1, you're looking at exponential growth. You'll dive much deeper into exponential functions later, but it's a good preview to see that different patterns in data lead to different types of equations. Let's summarize everything we've learned and then tackle an exit question to see if it's all clicked. Today, we've focused on change in tandem. We learned that this involves 2 linked variables, which we model with a function y equals f of x. We stressed the importance of defining your variables with units. Our main tool for measuring change was the average rate of change, calculated as f of b minus f of a divided by b minus a. We saw that on a graph, this corresponds to the slope of the second line between 2 points. Finally, we learned to identify patterns in tables. A constant difference means linear growth, and a constant ratio suggests exponential growth. All right, for our exit question. A runner's distance d in miles after t hours satisfies d of 1 equals 6 and d of 3 equals 18. First, find the average rate of change from t equals 1 to t equals 3. Second, interpret what that rate means. Take a moment to solve this yourself before we go over the answer. Let's check your work for the exit question. First, for the average rate of change. We use our formula, plugging in t equals 3 and t equals 1. This gives us d of 3 minus d of 1 divided by 3 minus 1. We were given that d of 3 is 18 and d of 1 is 6. So we have 10 minus 6 divided by 2. That's 12 divided by 2, which equals 6. The average rate of change is 6. But what does that mean? This is where our unit analysis and AP phrasing come in. The output is distance in miles, and the input is time in hours. So the units are miles per hour. This means that, on average, the runner ran 6 miles per hour during the interval from 1 hour to 3 hours. Using our template, for each additional 1 hour, the runner's distance increased by 6 miles, on average. So, we have successfully identified the variables, calculated the change, and interpreted its meaning in context. You've now met our learning objectives for today. Great job!